Okay, so here's another, and probably the last for this class, lecture about planarity. So, recall from last time, we showed that K5 and K3 are not planar, that they cannot be drawn in the plane unless you're going to allow edges to cross over each other. And we also showed that if a graph has at least 3 vertices and it's planar, then the number of edges is less than or equal to 3n minus 6. And I guess I didn't write this here, but m is the number of edges. Typically, that's the letter we use for the number of edges. So if I ever start talking about m and I didn't say what it is, it's probably the number of edges in the graph we're talking about. But I'll try to say it whenever I remember. If in addition, so meaning in addition to the above, meaning G has at least 3 vertices and it's planar and it's bipartite, in that case, then M is even smaller than this. In particular, it's less than or equal to 2n minus 4. And actually, these two things are how we showed that K5 and K3 are non-planar. We said, well, if K5 were planar, then the number of edges would be less than or equal to 3 times the number of vertices minus 6. And we found that that wasn't true, and that's how we concluded that K5 can't be planar. And then for K3, we checked this one, because K3 is bipartite, of course. So this is some good information. So let's take a look at a particular graph and just ask if it's planar. So here's a drawing of a graph, and of course the way it's drawn, there are crossing edges. It's really just these two edges that are crossing over each other. If I had drawn a graph where there's no edges crossing and asked you if it was planar, then that would be a silly question because the answer would definitely be yes. Like if I give you a drawing in the plane where there's no edges crossing, of course it's planar. That's only possible to do if it's planar. But if I give you a picture where there are edges crossing, then it's not clear. Clearly, this is not a good drawing. I mean, we can't use this drawing to show that it is planar. However, it might still be possible to draw the graph in a different way where the edges aren't crossing. So let's check something simple. Let's check the simple reasons that we were able to use in order to conclude that K5 and K3 were non-planar. In particular, let's just take a look at the number of edges and vertices and check if it satisfies this inequality. Well, this graph has 5 vertices. And if you count up the edges, there's 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. And if it's planar, then we should have m less than or equal to 3n minus 6. And we check this. 3 times 5 minus 6 is 9. 8 is less than or equal to 9. So what does that tell us? It tells us maybe. It tells us the graph might be planar. We know that if the graph is planar, then it has to satisfy this inequality. But this is not a double-sided implication. This is not an if and only if statement. Just because it satisfies this inequality doesn't necessarily mean that it is planar. If it didn't satisfy this inequality, then we would say the answer is no immediately, and that's how we concluded that K5 was non-planar, because it didn't satisfy this inequality. Okay, so we still don't know the answer, but actually so what I'm trying to get at is there's 2 ways this can go. You have to think of a reason why it's not planar, or think of a reason why it is planar. And of course, if you're looking at a particular graph and you don't know the answer, you might try doing one of those things and then run into trouble and say, well, okay, I tried showing that it isn't planar, and that's not working. Maybe that means that it is planar. but you try different things. So if we tried showing that it isn't planar, and that didn't work, let's try to show that it is planar. And that basically requires a different method. To show that a graph is planar, you just try to redraw it. And actually, in this case, it's not that hard. I didn't give us a big graph to deal with. There's really just the two bad edges. If I could just rearrange it so that these edges aren't crossing each other, I would be fine, as long as I don't create any new problems. So let me just do that. What I notice visually is I can keep, let's say I just want to change this edge. I'm going to keep all the other ones the same. And I just realized that if I want to get from this vertex to this vertex without crossing any edges, I can go around this way. And that's all I'm going to do. I'm going to leave everything the same, except for this would be the last edge to draw. And instead of going through here, I'm just going to go around here. That's the same graph, and now it's drawn with no crossing edges. So now we know the answer. Yes, it is planar. So if I give you a question like that, I give you a particular graph and ask you if it's planar, you will have to justify your answer, and basically I don't want to say the only way to justify a yes answer, but almost the only way I could envision you justifying that the answer is yes is to just draw the graph in the plane. If you're going to tell me the answer is yes, it's hard for me to see how you would justify that, or why you should justify that in any other way than just drawing the graph in the plane. That's typically the way to show that a graph is planar, is just show me the drawing of it in the plane. To show that it's not planar, you have to think of some reason, think of some property that the graph has that shows that you would never be able to draw it in the plane. And we talked about a couple of those, like checking this inequality m is less than or equal to 3n minus 6. We're going to learn more of that today, though. We're going to learn more ways to conclude that a graph is non-planar. So let's talk about this one. Is this graph planar? And let me explain this graph a little bit. It looks a lot like just K5, right? I've got these 5 vertices, and I drew all these edges, but there's something funny happening over here. K5 would be if I just had an edge directly from here to here. I wouldn't have these extra vertices, and that's what K5 would look like. But instead of that, I have this long path. It's like 1, 2, 3, 4, 5, 6 vertices on the way from here to here. And that's what this graph is. So we can check the simple thing again. Check whether m is less than or equal to 3n minus 6. This graph has 15 edges if you count them, and 10 vertices if you count them. And we're checking whether 15 is less than or equal to 3 times 10 minus 6, and this is like 24. And so it is, and then so that tells us again maybe, because if it didn't satisfy that inequality, then we would say no. And we can try following along the same kind of route that we tried last time. We checked whether m was less than or equal to 3n minus 6, and we found that it was, and then so we said, okay, let's try to draw it in the plane. We could do that to this one, but you're gonna have a hard time. Try as you might, you will not be able to draw this graph in the plane without edges crossing. And I know that because I know that this graph is non-planar. I know that the answer to this question is no. But what I'm getting at is what is the reason? The reason is, and I'm going to get more formal about this, this graph is a subdivision of K5. If I were able to, okay, think about it this way. If I were able to draw this graph in the plane without crossing any edges, then I could draw K5 in the plane. Because, like, however this long path gets drawn, I could take the drawing of this graph and turn it into a drawing of K5 just by kind of erasing these vertices. Like, instead of drawing this long path, I would just draw a single edge. In whatever way it's drawn, I'm imagining that we've drawn this graph in the plane, and then I can turn that into a drawing of K5 in the plane by just turning this path into a single edge, which would transform this graph into K5. And that would be a drawing of K5 in the plane, but that's impossible. So the answer to this question is no, the graph is not planar. And I'm going to explain that more formally in just a second. Okay, here we go. That was fast. Suppose we have a graph G with an edge, UV. We can form a new graph G prime, and we say we're forming it by subdividing the edge E. And formally, this is what it looks like. The new vertex set, the vertex set of G prime, is going to be the same vertex set as G plus a new vertex that we call W. And the edge set of G prime is going to consist of all the edges of G. Except I'm going to remove the edge that I'm subdividing, UV. I'm going to remove that one, and then I'm going to put in two new edges from U to W and W to V. And remember, W is the new vertex. That is overly technical. It's an overly technical description of an intuitive concept. Here's the picture that's more intuitive. In G, you have this edge, UV, and of course, G is any graph. It could have other vertices that I'm not drawing and other edges that I'm not drawing, but this is in the graph somewhere. In G prime would have everything else the same, so all of these other vertices and edges that I'm not drawing in G, those would still be all here. Nothing would happen with those. The only thing that happens is, instead of having an edge straight from U to V, I go from U to W to V, where W is a brand new vertex. So it's visually it's as if I just took this picture and drew a dot in the middle of this edge and called it a vertex. So it's a lot more intuitive than this technical description makes it look. If you do this repeatedly, like if say you have a graph G double prime and you form it by starting with G and then doing any number of subdivisions of edges. So you subdivide an edge and then you take that graph and maybe subdivide another edge and then another one, and you do this several times. The resulting graph, we just call that graph a subdivision of G. So in this language, the graph that we talked about a minute ago, this is a subdivision of K5. And the reason why we're talking about subdivisions is that, well, we're talking about planarity, and if one graph is a subdivision of another, then either they're both planar or neither one of them is planar. Because subdividing edges doesn't really make it any easier or harder to draw the graph in the plane. Again, like, if I can draw this in the plane, like, and imagine again that there's other vertices and edges that I'm not drawing, but if I can draw all of that in the plane, then I'm going to be able to draw this in the plane, because I can just take whatever drawing this is and just alter the drawing a little bit by putting a dot in the middle and calling that a new vertex, and that will be a new drawing with no edges crossing of the subdivision. So subdividing edges doesn't have any effect on planarity, so to speak. So if K5 is not planar, then this is also not planar. So now we get to a very powerful theorem about planarity, and this is something that I'm not going to prove. There is a proof in the book. It's a bit tough to follow. We prove it in the grad. I'm not complaining about the proof in the book. I'm just saying that Kuratowski's theorem is not something that's easy to prove. When we prove it in like the graduate level class, for me it usually takes about a week to prove it. You have to kind of build up a few facts and prove each one, and it takes a while. So I'm not going to prove it in this class. I'm just going to state it. But like I said, this is a powerful theorem, especially in the sense that it's an if and only if theorem about planarity. It tells us that G is planar if and only if, well, I guess I'll just keep reading. If and only if G does not contain any subdivision of K5 or K3 as a subgraph. Now, I call it powerful because it's if and only if. One direction of this is not too hard to understand. We can understand one of these directions. I think we can understand the forward direction. The forward direction is just saying that if G is planar, then G doesn't contain any subdivision of K5 or K3 as a subgraph. And that should be clear enough, because if G did contain a subdivision of K5 or K3, then, well, these are not planar. We know that these are non-planar, and so then any subdivision of those would be non-planar. So then how could G be planar? So we do know that direction. We do know that if G is planar, then it can't contain these subdivisions. What takes a lot of work is proving the other direction, to prove that just because G doesn't contain either of these, let me start over. Just because G doesn't contain any subgraph that's a subdivision of either of these, why does that mean that we can automatically draw G in the plane without any edges crossing? That's most of the work in proving, and that's what I won't really get into in this class. But we can use it. So let's take a look at this graph. This is a famous graph. This is called the Peterson graph, and actually it's SEN with an E there. But right, so this is the Peterson graph, and as you may have guessed, I'm going to ask the question of, is it planar? Well, since we always do this, let's check the easy thing first. N would be 10. M would be, okay, let's see. I've got 5 edges in this star, and then 1, 2, 3, 4, 5 edges like this, and then 5 more edges along the outside. So I would say that's 15 edges. Actually, I think that's the same. Yeah, so, well, we dealt, I'm just noticing we dealt with these numbers before. This is true. 15 is less than or equal to 24. So the truth is, this isn't a very good test. Every time we've used it, it has told us maybe. There are some situations where it definitely tells you the answer, but we haven't had very good luck using this test today. So we don't know the answer. This graph, okay, let me start over here. Of course, when you look at this graph, most people notice that at least vaguely, it kind of looks like K5. I mean, I have 5 vertices in the middle with this star-looking thing. Yeah, maybe it's hard to explain the vague similarities that it has, but it just kind of looks in some ways like K5. We're not going to find a subdivision of K5 in there, though. And I'm more specifically, it's not, maybe I'll just go off in the corner here. Here's actual K5. It's not actually possible to subdivide edges in any way to turn this into this. I mean, subdividing an edge, all it does is it just sort of takes an edge and maybe it turns it into a longer path. So when I subdivide edges, I can make something that looks like this. That's kind of all I can do. In order to turn this into this, I feel like I want to do something else where I'm like taking this vertex and stretching it into these 2 vertices, but I'm not allowed to do that. Like that's not edge subdivision. I can't turn one vertex into 2 vertices. So where does that leave us? Well, still the answer is maybe. We don't know. If I were able to turn K5 into this, or a subgraph of this, by using edge subdivisions, then I would know that the answer is no, it's not planar. But I'm not going to be able to do that. Here's what I can do, though. I had to very carefully draw this in advance. I can find a subdivision of K3 in the Peterson graph. So I'm going to flip pages again. What I've drawn here is a subgraph of the Peterson graph. Not all of the edges are there. Like, the Peterson graph would have this edge. It would have this edge. I guess those are the only 2 edges that are missing. But in any case, not all of the edges are there. And I claim that there's a subdivision of K3, and you have to follow this carefully. So there's 3 blue vertices. I'm not sure how well this is showing up, so let me even put B's by the blue vertices. And then there's 3 red vertices. Because what does K3 look like? K3 is supposed to be like you have 3 vertices on one side, 3 vertices on the other side, and then you have every possible edge in between this set of 3 and that set of 3. Of course, we're looking for a subdivision of K3. So this is what a subdivision of K3 looks like. And I'm using the color codes to indicate these 2 sets of vertices. Typically, when we draw K3, they're sort of arranged visually, like I put one set on the top and one set on the bottom, or maybe often it's like I put one set on the left and one set on the right. But of course, you can draw a graph however you want. And so we have to be a bit creative in how we look for a subdivision of K3 in this graph. But that's the purpose of the color codes. So that's what red and blue represents. And what do we need to do here to really show that this is a subdivision of K3? K3 is supposed to have an edge from every red vertex to every blue vertex. And if it's a subdivision of K3, that edge might turn into like a path. Like, so instead of having an edge directly from this red to this blue, I have this path from this red to this blue. And so I just have to find paths from every red to every blue. So, and that's what these edges are for. Like, for example, let me just check that I can find a path from this red to every blue. Okay, I can get to this blue by going this way. I can get to this blue by going this way. I can get to this blue by just taking a single edge, and that's fine. It doesn't have to be a longer path. It can be a single edge. Okay, let's check that I can get from this red to every blue. I can get to this one, I can get to this one, and I can get to this one. Let's check that I can get from this red to every blue. This one's easy. I can get to this one, and this one. Those are all just single edges. So that's it. That's a subdivision of K3 in the Peterson graph. So for this one, the answer is no. All right. So let me just finish up quickly with talking about drawing graphs on the torus. So a graph can be drawn in the plane without crossing edges if and only if it can be drawn on a sphere. Like, you can think of a sphere, and if you can draw it in the plane, then you can draw it on the sphere, and vice versa. But there's things that we can't draw on the plane and that we can't draw on the sphere without crossing edges. So sometimes we talk about drawing them on different surfaces, and I'm not going to talk much about this. This is kind of just indicating that there's a big world of math out there. There's more to learn after this. So let's talk about K5 on the torus. As we know, it's not possible to draw K5 on the plane, and it's not possible to draw K5 on the sphere, but it is possible to draw K5 on the torus. So here, this is a bad start. I was trying to draw 4 vertices, and if I draw a 5th vertex, I'm not going to be able to get to all of them. So this is a bad start. And my video is running out of time here, so I'm just going to have to go quickly. Here's 4 vertices. I'm going to get to this one like this. And then I'm going to draw a 5th vertex, say right here. And that can be adjacent to this, this, and this. And it still needs to be adjacent to this, but I can go around this way. Like I'm going around this part of the torus. So that's 5 vertices, and they're all adjacent to each other. So it actually is possible to draw K5 on the torus, even though we can't draw it in the plane.